pro of something is not a presentable category. So this is sort of, essentially how this is how we build on mathematics. Like sets have elements and they're unions of their elements. They don't have co-elements, they're not products of their co-elements. There's a sort of fundamental asymmetry here. What we like is categories that build up using direct and filtered coordinates, not inverse limits. Right. So looking at but still, like we like to say, okay, Banach spaces are nice building blocks of functional objects. We might like to keep those. So how do we fix this? Well, there's sort of two obvious things to do.
Can I ask the question from left field? The reason we like in conditions is for they're very good for mapping past, but pro things are very good for mapping in. And here it looks like we're building the targets. So why would pro things be good for mapping in? No,
that's it. I was just going to say that's a question that is going to require some more pondering that I can do. You can do two things. You can just replace pro with in Banach spaces. Also, you also get a category that's built out of Banach spaces, in a well-controlled way. So these are essentially in the same way that locally convex spaces are essentially pro Banach spaces. These are essentially so-called chronological vector spaces. Instead of axiomatizing the notion of an open set, you axiomatise the notion of a bounded set. What you can also do is take the opposite, like pro ban up, since that's in of ban up. This is a slightly less classical, less familiar category of functional analytic gadgets. Usually, there's a certain equivalence in functional analysis called stereotype duality, which relates to a class of objects called Smith space, which I'm also not going to explain. So at this level, these two options are dual to each other in Europe. Yeah.
What's actually convenient for
Right,
which added a lot of different categories.
I'm going to. This is like these are sort of two options, but in the literature, I'm going to pick one. I'm going to motivate this. You got it.
What's nice about it?
Well, these are these in particular. They're both sort of if you put some conditions on Banach spaces, they're presentable categories. You have all limits and co-limits. You have adjoint functor theorems. There's a very well-developed theory of categories enriched in such presentable categories. Yes. Well, these two are Cullen exact categories. This is exactly what I'm gonna sort of. These two are Cullen exact, but they're not abelian. And so abelian completion yields two. I mean, here is the word "the," but maybe that's two tracks of modern approach to functional analysis. Well, like neither of these categories are abelian. But again, to be in a if you want to place yourself in a convenient categorical setting, it's nice to have an abelian category. You can work with, but then if you do homological algebra, like you stabilize, you get a derived category that has a heart, and what you're essentially doing is just working with this heart, and it's useful to, at least psychologically useful to understand this heart. So this collection of authors, or Basat, with Kobe Kemnitzer and also Jack Kelly, what they do is they take this the so-called the smallest abelian completion of the first option in Banach. And so by abelian completion, I sort of mean with respect to this Cullen exact structure. You have a bunch of short exact sequences, and you look at the smallest abelian category for which the embedding preserves those. Dustin and Peter Schultz, I sort of, if I say something which you don't agree with, take the other option and do a more complicated abelian completion, where, well, yeah, where you explicitly introduce non-locally convex objects. this gives you the category of liquid condensed. So that's another story, but I like the first one better. So this option is a little bit easier, at least sort of is a historically a bit more classical. And I think there's some technical advantages here because you explicitly put yourself in a place where you lose the affordances of local convexity. And sort of, for instance, what I really want that, like, if I take the ring of smooth functions, I'd like the derived dual of this to be distributions, and I don't want there to be any higher x's. And this is true in the, but
no, independent of ZFC.
Well, yeah, I'd like to. Yeah, so this is I think in option one, this is true.
No, it's still independent of ZFC.
It's
Calculations are exactly the
Oh,
same.
but
Nuclear things, it doesn't matter what you choose. It's independent of ZFC.
Oh, but don't, like, aren't all your short exact sequences in option one sort of you
But this is not Banach. I mean, this is not Banach. So to calculate this x, you have to write it as a colimit of Banach space. It's a very complicated colimit diagram, uncountable. And the poset structure depends on. I mean, the question of cardinalities of cofinal subsets of this uncountable poset, I think, depends on axioms of set theory. Really, the answer can be different depending on your model for TF.
Yeah, no,
either have higher x or you cannot.
That's what I thought that was what's going on in option
It's
two.
the same. It's exactly the same in Banach.
Okay.
Now the other way around is always true in both settings. The derived dual of the distribution is.
Okay, I'll ask. Okay, well, I'll ask you to explain.
Okay. Yeah.
Okay, so let's talk about this abelian envelope for a second. So what is this abelian envelope? So this is this turns out to be the category of right modules for endomorphisms of a generating projective. And the projectives in the category of Banach spaces are well understood. If you look at Banach spaces that contain a dense set of some cardinality smaller than kappa, then this category has enough projectives. And an object projective exactly if it's a space of absolute sum of the seeds. And it turns out to be that this abelian envelope is just the category of right modules, ordinary right modules for endomorphisms of this object L1. And yeah, so this is what I said on the previous slides of that Indo-Ban is this envelope, but that's not quite right. Like, you have to make one of these cardinality restrictions. And for now, I'm going to pick the smallest uncountable carbon, and that suffices for all. And so, what is this algebra of endomorphisms? That's just an infinite matrix algebra. It's countably infinite square matrices where all the columns are absolute summable sequences, and the row of absolute sums is a balance. And these two conditions tell you that matrix multiplication can converge. In the end, this category, this abelian envelope is something very simple. And this category, this is a very old category. This is not new. This was introduced by a functional analyst, Lucien Waldburg, back in the 60s. And recently popularized by these three authors, Steffens and Pelle. So how should you think of this? Well, you should think of an object in this category as a vector space together with some formal set of bounded sequences, which you can, and these bounded sequences you can pair with these L1 infinity matrices and produce new bounded sequences. So I'm going to give this a name. I'm not claiming that I made a new contribution here. It's just that I don't want to say the abelian envelope of infant all the time. So I'm going to call this structure an aggregated vector space. And that's this category, right? So this is an obvious derived infinity category. You just say right modules to this infinite matrix algebra in spectrum. And that's what we're going to be working with. And the the usual category of locally complex spaces doesn't embed fully faithful in here, but it is fully faithful in a very large class. Locally complex space. So in particular, all Banach spaces, all persist spaces, all the duals of persist spaces are fully faithfully embedded in this category. What you just morally what you do is you take a vector space with topology. This gives you a notion of Banach sequences, and that's your aggregated structure. So this has a tensor product because this category is by definition projectively generated by space L1, and the projective tensor product of Banach spaces on these L1 spaces is very simple to define, and you just declare that it has to be Banach elements. Right. Like if you that makes this category a commutative alpha object. So this also gives you right away notions of topological, maybe more accurately borderlogical n vector spaces. So you can feed this into the construction into this machine. The hybrid category produces for you notions of higher topological. So maybe let me recall for you that. So in for n equals 2, so the objects what are these? Well, they're locally constant factorization algebras. On RT, so these came up in Damian's talk on Wednesday. So this is a Gaussian that assigns to any, for instance, any disk, it assigns an object in this category. So to any disk, you assign a category enriched in this category A mod. And this can move around, and this produces for you a notion of graded topological category. Yeah, yes. Yes. Why do this work? I will use NPR when I'm going to talk about there's two constructions with VFTQT. One, for one, I'm going to use some reliability rules. And when I'm going to talk directly, then these objects, sort of the one-morphisms, are locally constant or constructible factorization algebras on pictures like this. So there's three kinds of disks: a disk here, a disk here, and a disk here. And so here's a category, here's a category, here's some line module category, and two morphisms sit on pictures like this, where now there are 1, 2, 3, 4, 5 different kinds of disks. And I should mention that we're using recently developed notion of factorization algebras where we don't allow embeddings from the empty set into the disk that contains the point. This sort of we're using factorization algebras that are pointless, which means exclude embeddings like this, and this was introduced by Claudia's thesis, Island Carlson. Like Claudia's thesis student, Island Carlson. And so something that we now like to do is define like a category of aggregated smooth G representations that contains at least all smooth G representations for Shea spaces, but also something like duals of this distribution from G. And so how we're going to do this? So here's a theorem that we've been talking about for a while now. This is finally done, so I don't want to hype you up too much, but keep a close eye on the archive digest next week. So an object in this reader category is this is an n+2 category, and in here is n+1 dualizable, if and only if the category is dualizable as a marginal category for all its factorization model. Right. So you think of an object in this category as something living over R2, and you can integrate it over the sphere, integrate over spheres of all lower dimensions. And these are algebras that act on C. And if you check that the original object is dualizable over all of these algebras, then you're dualizable. So this generalizes. So this, as probably we generalize a result of I think was Shea, David Jordan, and Noah Snyder. So to be n+1 dualizable, it suffices to be rigid. And here I mean rigid in the sense of gauge theory. So what is rigidity? Rigidity is just a very strong form of self-duality, which is inherited by many operations. So if you are n-monodial and you're rigid, then you're dualized on self-dual, also as a marginal category for all these factorization models. So what is gauge theory rigidity? Gauge theory rigid if you're if you have some enriching category V, then your category V is gauge theory rigid if the associativity square is right adjointable. So these vertical maps here have right adjoints. This has to be internal to the category of V enriched categories. And the composite of the unit with this right adjoint is the co-evaluation of duality. So if you are in a more classical situation, if you are in a situation where V is the spectra and V is compactly generated, then gauge theory rigidity is usable rigidity. Every compact object has a left and right dual. But the categories that I'm going to talk about, these categories representations for compact groups, they are not compactly generated. Quite far from compactly generated, but they will be rigid in this sense. They will be rigid in this category of categories enriched in topological. So how do we do this? So, like I said, we want to define rep G as just Q code BG, but now for some good notion of Q code. Well, when you have a manifold, you can think of the sheaf of smooth functions as a sheaf of aggregated integrated algebras, and as such, you can take its sheaf. You can take a point. I can tell you why should you do this? Why is this the right notion? Apart from stupid ash that the theorem will work out. But for now, we take this as given. And so Q code itself is now a sheaf with values in the category of symmetric monoidal categories in which topological and the functionality is pulling back to quasi integration. And this has an important base change property. So whenever you have a proper pullback diagram of manifolds, you get a right adjointable square. I think maybe the battery has run out. Dead. And so this right adjointability is exactly something we want for this notion of theory.
What's your hypothesis on the pullback square?
So say the map from Y to W is a proper map in the usual topologies.
But then there's no, you want to say it's transverse as well, or?
Since I'm working with manifolds, yes. So if in the setting of derived manifolds, you would not have to use that. You would not have. Yeah. So this notion of Q code, this is most naturally defined on this larger category of derived manifolds. In which case, no transversality assumptions are needed. Yeah, I think it has completely. Okay. Yeah. So now, give yourself a Lie group. Look at the classifying stack, or more generally, give yourself a Lie groupoid and look at the quotient stack. The nice category with all adjectives presentable symmetric monoidal category G representations is this category Q code of this quotient stack. So by definition, that's the limit of. I should not point at this CP because you won't see. By descent, it's this limit diagram. And if you do this for a Lie group, what you can show is that this category of G representations is exactly this co-modules for the Hop algebra of smooth functions. Smooth function is now a Hop algebra object in this category of aggregated modules, and you can write down symbols. And so this tells you that this category contains exactly what you like. For instance, what is this C infinity G co-module structure on a Frichet space? Well, it's a map like this. This map is adjoint to a map G times V into V, which is a G representation. The fact that it comes from a map like that tells you that it's. Here's another characterization. You can also write this category as right modules for the non-unital convolution algebra. And you have to take special kinds of modules, so-called H-unital or firm modules. Make this work. And so probably a version of this also holds for the Lie groupoid case. So, the claim is that this is that this category QCO of BG or AREP G is gauge-theory rigid. So here's a theorem that, I mean, maybe I think this argument maybe goes back to Justin. I don't know. So if you take a Lie group or a properly groupoid quotient, then this map. The map you get from the canonical X-model structure of QCO, this map is an equivalence. And in algebraic geometry, this is true for any reductive group, but in differential geometry, you have to put some compactness assumptions. So this in particular depends on the fact that there are normalized high metrics on this. This does not work for GLN. And also, like this equivalence would completely fail if you did not use this this topologically enriched set. So as a corollary, this category QCO of X, in this case QCO PG, is gauge-theory rigid because what you just do is you apply a proper base change to this very simple Fulbright diagram. Then I think this argument probably goes back to gauge-theory. I don't know. But I say if you just hit this diagram with QCO, you get the square in the definition of rigidity that was supposed to be right from. And yeah, so QCO takes these products to the center products, which is by this theorem. And I will stop here. I fortunately don't have time to talk about the quantization construction as usual, but feel free to talk. Questions?
Is there a topos for which your vector bases are just the vector phase on X?
I don't think so. I know that like these authors that like so they're working on some version of sheets on sets with nodes. Like you can take sheet on these and then look at really group objects in there. But that's a much larger category.
So this have to work with as well as those original of the center. Trying now to know that it's and also So somewhere in the little woman is saying. This why wants to.
But did they like have to make for the exponentially faster what parameter is and probably is this is no longer because I think it's a bit hard for me. This is no longer can be possible. Right, right.
You didn't realize the unusual algebra success.
Yes, but I do mind them in when setting up.
Let's all hit the speaker again. We'll be back in a few minutes. Are you going to come to?
I don't see question. We had think about all of this stuff is what I found. It's like the you still have the like the example the effects are still things are sort of on the extended. You still have like the what we're trying to but we're trying to say also yes, absolutely. That's that was what's going to be. So just I definitely want to but there's some source there just so people know. Let's go ahead and now. It's kind of like I just guess I knew that most of it was that. I don't know what probably has to okay, I guess touch on this. I'm just gonna ask. Yeah, so and then clarify it. Yeah. Don't that's not how so if you were bed, thanks a lot. There's like I want it might be time to go now, but it's not I don't know what it is. Well, people use actually respond by your meeting. I don't know. I don't know if this is or there's sort of like there's work on it. Like there is a very there's 100
There's a pointer, there is a tiny laser pointer. That you press the button from the slide, but you have the slide. I think you can to slide the others. And this is a tiny. Actually, yeah, that's like a little bit worried that I will not have. So this one fits more straightforward as I think.
So you do, I mean, you can like take like bigger parts. Yeah. And now it would be like
So I have a,
We should probably start asking.
Great. Please join me in welcoming Lukas, who's going to tell us about fully local unitary topological quantum field theory.
Yeah, thanks for the invitation. Thanks for coming this early. Thanks for sticking around for my talk. I'm going to talk about combining the notion of fully extended CFT, as for example in Pelle's talk, and many other talks with notions of unitary. And I hope this will be at least a bit understandable. I was trying to be a bit more pedestrian than usually talks about this. So it's based on various papers. There's like a big paper with many people, which somehow set out some of the ideas and make some proposals on how the story should go. Then there's the recent paper with Leo, Dave, and Luke, which appeared on the archive a few weeks ago, with those are my only look at it.
Yes.
Which appeared a few weeks ago, which just looks at notions of two-level spaces. I'm not going to use much of it, and then most of it is ongoing work in progress with Cam, Theo, and Luke. So this is what we will get to towards to the end. So I know you owe you a bunch of apologies. The first one, as it's been formed, I have not really been sleeping well. I think probably many of you haven't either. So I'm not probably as sharp as I would be usually, so I might say something which I don't. I apologize for that. The next thing to apologize for is that I have handwritten slides. I made these on the train when coming here, so they're a bit more shaky than they would be normally. So I'm also sorry about that. And then the last thing to apologize for is that I've not included an appropriate amount of references. So there are many things many people in the audience have been working on, especially from the physics side, which is not appearing on my slides. And I apologize for that as well. So let me just set the stage. So what I want to talk about is what does it need to be unitary and extended at the same time for topological field theory. And like in the setting of the conference, one place where people care about topological field theory is this notion of the symmetry TFT, where the idea is that if we have some quantum field theory F, and we want to understand its generalized symmetries, we can understand those by finding an 1 + 1 dimension, n + 1 dimensional TFT together with the topological boundary, which tells us anything we want to know about symmetries. This is what's called the quiche sometimes, and this is really what replaces in the study of ordinary symmetries the notion of the group. So this is the type of what is the symmetry abstractly, and then in addition to realize it in a system, one needs to find these additional boundary conditions F, which are non-topological, and they correspond to a representation of the symmetry or a module of the symmetry. So the concrete realization of symmetry in a non-physical system. And so if you think of these features as abstractions of the notion of the group, you might ask what is something like a group element. And what they correspond to are topological operators in the system of the bike and the topological boundary. And I just want to make the point here that if you care about topological operators, the non-extended notion of TFTs is really not what you should consider. Because in a topological field theory, one motivation to extend is to get things like operator state correspondence. So if I want to ask what is a point operator in a TFT, I can understand this by cutting out the sphere around it and looking at the state space on the sphere. But now I have some extended operators that say I have a line living on the boundary here, and I ask what is the category of these lines? One way of understanding is just to cut out a link around the line. These would be these two dots here, and then something living in Z. And my extended TFT will assign some type of category to it. And there's a version of the operator state correspondence or extended operator state correspondence, which really says, oh, this category is the category of line. So if I want to understand this picture fully and then also ask what are unitary representations of these generalized symmetries, if I want to approach this from the sim TFT, I really need to have unitarity at all levels to figure out what happens with these extended operators and not just at the level of Hilbert spaces or vector space. This is, yeah. So I mean, this is already what I alluded to. One way, so it's not fully clear to me at least what it means to have a unitary representation of the generalized symmetry. But if you have this picture, one natural guess would to just say, oh, everything in here is a unitary cube. And then you call that a unitary symmetry of a unitary representation of your extended. And then from that perspective, you just ask, oh, what does it mathematically even mean to talk about a unitary extended? And another motivation, which is somehow purely mathematical, is that often we think of topological theory as doing representation theory for manifolds with respect to this operation of cutting intervals. And whenever you study representation theory, it's also often important and more helpful to study unitary representations. For example, they have some better behaved properties. They are naturally symmetrical, things like that. So just asking from this analogy, you should at least ask yourself what are unitary versions of this representation. But let me set the stage by first explaining what does unitarity mean in non-extended theories. And I'm really doing, I'm really working in this Euclidean setting, so I'm talking about reflection positivism. So just the Euclidean version of unitarity. I'm mostly following the proposal by Friedrich Hopkins, their description of the story. There's a lot of work on it, which I'm not going to refer to. But so as a definition, it has two parts. It has a reflection part and a positivist part. And the place where the story started in the work of Oswald Schrader is we look at some operator living on some Rn, and we pick some hyperplane H. And what I can do is I can take this operator and I can reflect it along the hyperplane, get an operator sitting on the other side, and then in my QFT I can compute its correlation function. So I compute the correlation function of O and the reflected version. They argued that this should be define the Hilbert space pairing for the state space. And since I want to have a Hilbert space, this pairing should be positive definite. So reflection positivity means that if I compute these correlation functions, they always should be positive definite functions. And one way of seeing this is that if I have a situation like this, I can formally perform a path integral over from minus infinity to h. This will generate some state in the Hilbert space of the theory on the hyperplane h. And then this correlation function is just a scalar product for the Hilbert space. And in DFT settings, we prefer working with compact manifolds, at least axiomatically. So if I take this picture and I compactify it, I get two disks glued together along a circuit. I have an operator sitting at the origin of one disk. I have the reflected operator sitting at the origin of the other disk. And I ask the partition function of my DFT to be larger than this. Now for DFT, we consider more general manifolds than just disks. So in general, it might be natural to ask for a manifold of this type, also to satisfy similar positivity, where if I do a path integral over it, I generate a state in my Hilbert space, and then the inner Hilbert space inner product is given by taking the manifold, gluing it to its reflected version, and computing the partition function. So again, we want this to be positive. And I mean, in some sense, you can also use an operator state correspondence, but this whole manifold will correspond, generate some operator over acceptance. So these two definitions are somehow the same, but from a conceptual point of view, this definition seems a bit more easily to implement in the experimental framework. And what Friedrich Hopkins and others thought about is how to implement this for functorial theories. This is a mathematical language I'm going to use throughout the talk, and I will move on to extended one. So this, I mean, you probably have, most of you have seen that, but the definition is in terms of a symmetric monoidal functor from some borders in n category to vector spaces. And for simplicity, my borders will always be oriented until the last byte. So in the objects here are just manifolds of dimension n-1. The morphisms are given by so-called cobordisms between them, which are n-dimensional manifolds which interpolate, and the composition is given by gluing. So if I glue these two manifolds together, I get like this. And then functoriality means that if I the functor will assign to each object a vector space, this we think of as the state space. and to each of these borders a linear map, which we think of as performing a path integral or time evolution in this direction. And factoriality, this means that the composition of these is the composition of that. And so the question is that if we look at this type of definition, how do we give it in this framework? And one thing to note is that we want these reflecting and doing together to be our inner product. The one fact about scalar products and Hilbert spaces is that they're complex antilinear. And the definition on the previous slide, there was nothing which even depend on complex conjugation. So nothing so far knows about it being like that reflecting should be complex antilinear. This is the operation of reversing the orientation on a manifold, but there's nothing which tells us that this is the same as complex conjugation. So to set up reflection positivity, we first need to say what does reflection mean, and we call it field theory or reflection theory if it intertwines orientation reversals with complex conjugation. So taking an oriented manifold and reversing its orientation gives me another manifold. So I have this manifold which goes from sigma 1 to sigma 2. I reverse its orientation and now goes from the orientation reversal of sigma 1 to the orientation reversal of sigma 2, and we call this a reflection. And the condition of a reflection theory is that this operation corresponds to complex conjugation. The complex conjugation gives me the two action on the category of complex vector spaces, and I ask my field theory to be equivariant with respect to that. This just means that if I look at the vector space on an orientation reversed manifold, I have some coherent isomorphism or some isomorphism to the vector space which I combine a complex conjugation. And then there are some conditions. One says that this is the two equivariant, so if I do things twice, I get the identity. And the other thing that I have some compatibility with manifolds. So if I look at the map induced by some orientation reversed manifold, this is the same as the complex conjugate of the map for the original manifold. In particular, if I look at maps out of the unit, so the empty set, we will see that the state many complex oriented manifold generates is the complex conjugate of the state the manifold generates. And with this, we can actually write down a pairing, which is now complex antilinear and one of the variables. So if I have my manifold M here, which generates a state, I can look at the complex conjugate, which generates the complex conjugate state, and to now construct this. So far I just generated two states in my Hilbert space, but now geometrically getting a pairing is to glue in a cylinder like the same cylinder. And then if I perform that, I exactly have this partition function, which is the glued-in manifold. And what's easy to show is that in any reflection theory, if I look at the pairing which starts with Z of sigma complex conjugate, uses the reflection structure to identify this with Z of sigma bar tensor sigma, and then I apply the morphism I get from this band cylinder to the complex number. This is always going to be a Hermitian inner product. From the conditions on the previous slide, the skew symmetry follows, and it's somehow non-degenerate by the usual bending argument for cylinders. However, in general, even in a reflection theory, there is no reason for this to be non-degenerate, to be positive. So we call the reflection positive if all these pairings are positive. And I should say that you might think, oh, this is a bit more than what we asked when talking about reflection positivity. But if you think of the operator state correspondence, somehow each element in here, you can think as being some operator living in the interior of sigma for something. So you really just ask that for all these operators, if I reflect them and I do them together, I get the inner product, which is supposed to be positive. To give a slight redefinition of the same story. Which is, so what I can also do is I can take my manifold, I can reverse its orientation, but then also reverse its input and output. So now this is a Fordism going the other direction, which I call M dagger. So it's just the orientation reversal, and then I use these cylinders to bend everything to the other side. So I get this, and in a reflection positive theory, you have Hermitian or even Hilbert inner products, and they automatically satisfy that if I evaluate my theory on M dagger, this is the adjoint of my theory evaluated. This is what's called a dagger function. Or there's also this notion of a dagger category, which is just a category equipped with an anti-involution, which is the identity on object and squares strictly to the identity on morphism. So from a category theory perspective, this is a quite inconvenient definition because it's not compatible with saying received by something equivalent. So these things are sometimes called evil, and I will come back to that, but for now it's almost on this. And then the definition I've given on the previous slide is exactly equivalent to asking my field theory to be a dagger function into Hilbert spaces, where on the Boston side I equip it with this dagger operation of orientation reversal, which reverses the direction, and on the Hilbert space side I use the adjoint of linear maps. And this makes classification slightly easier because you don't need to go through reflexive. You ask what happens in 2D. So we know that two-dimensional TFTs, non-extended ones are symmetric, commutative for linear algebra. So there are these maps, a unit, a multiplication, a co-multiplication, and a co-unit. And now unitarity just asks these things, the multiplication and co-multiplication and the unit and co-unit to be adjoint of each other. And an example is diagram-written theory. The vector space assigned to a circle are the class functions on some finite group. The co-unit is the valuation and the unit. The co-product is just pulling back along the multiplication. Then the unit and multiplication are determined by asking just asking them to be adjoint, so you will get the convolution product. And if you've seen some representation theory, you've probably seen this inner product on class functions, for which the characters are also normal for class. This really already gives you some hints that these theories really know about the unitary representation theory of finite groups. That's just the representation theory. So I've given you, I should say one other example. If I put in a unitary fusion category and look at the Tuapiro theory, this will also be unitary on this time. So I've given you two definitions of unitary non-extended TFTs, and I mentioned that they are equivalent. But then one of them used these notions of dagger category, which are inherently evil or not invariant under equivalences. So you might ask, where was this definition in the previous word? Somehow, when I stated the definition of Friedrich Hopkins, this evilness or the notion of somehow not being invariant under equivalences is really hidden a bit within the framework, and I just wanted to explain where it is. And for this, also to motivate some of the things showing up later, I want to talk about these things called Hermitian objects. So the setting is just we have some monoidal category which has duals, and then it has a symmetric monoidal category with duals. It has additionally two actions. This is this bar operation, which in our examples were complex conjugation or orientation reversal of the manifold. Then if I look at its core, so I forget all non-invertible morphisms, taking duals gives me a Z2 action, which automatically computes with this bar action. So I get a combined Z2 action, which sends the morphism from C to C dual to the dual morphism complex doing this involution and then taking an inverse. I need to restrict to the core so that I'm able to take the inverse. So that this operation of taking duals, I can actually turn it into a map between the corresponding objects. And now the definition of a Hermitian object is just a fixed point for this action. So if I'm in the setting that I have for something symmetric monoidal, there will be two action. I can have that what are the Hermitian objects. So I take this fixed point, and it's a fixed point, so it's an isomorphism from acting to the original object plus some coherence conditions. Or equivalently, since the dual can be characterized in terms of the evaluation, this is a map from C bar to C dual, or giving an evaluation, and then the coherence condition is that if I apply C bar C, I do a flip, and then I can apply the dual as a complex, the bar of the evaluation. I want to get the original evaluation. This is exactly the skew symmetry for Pelle. And for this, you need that these are the two actions just so that this will be even possible. And now you can ask, what are these things if I start with complex vector spaces and complex conjugation, and you find Hermitian structures. And in the bottom category, these bent cylinders we've looked at before, they define Hermitian structures or not. And it's reasonably easy to see that any reflection theory will preserve Hermitian objects. So what we really did is for every object sigma, we picked a Hermitian object we like, which is this one, and we asked that the Z2 equivariant reflection theory maps this to another Hermitian object which we like, which are these coming from Hilbert space. And the choice of picking a Hermitian object as any Hermitian structure as any object, this is not functorial in C. Just because I had to restrict to the quarter, so it doesn't know about the morphisms in C, and this is somehow where in the definition via Hermitian structure the evilness comes in. And this is also why these two definitions are the same. So somehow here I really keep information. A Hermitian structure tells me how this operation of doing a dual bar is trivial on an object. And I cannot ask it to be trivial on the whole category because it reverses the direction of morphism. So it doesn't even make sense to ask something to be equal to something which goes in a morphism direction. This was my review of the Fried-Hopkins story and then a bit about the connection to data categories and Hermitian objects. Now I want to take this and combine it with extended series. So for various reasons, we like to continue cutting our manifolds to lower code dimensions. One motivation was this operator state correspondence. So if I want to, for example, ask what are line defects in a three-dimensional TFT, I can cut out a circle around my line, get a category assigned to it, and this will be the category of line. So in general, the story goes like this. On the top level, we get some complex numbers. If we go down one dimension, we get some state space. If we go down 2 dimensions, we will get some linear category, and then if we go on, we get higher categories. So the lower we go, the higher our category number goes. And from a mathematical perspective, one reason we like these extended series is that they are classifiable. So the bottom gives somehow an algebraic characterization of field series out of these Bordison categories, or gives an, somehow a universal property for this Bordison category. And so in general, this will lead to an N category where the objects are points, one morphisms are one-dimensional Bordisms between them, two morphisms are two-dimensional Bordisms between those, and so on. And we will for a while just focus on dimension 2. So here the objects are, as I said, points. One morphism are the Bordisms between them, and then two morphisms are co-Bordisms of those. So here I have drawn a Bordism at the bottom, one at the top. These are these two things here. And then a two morphism between them is some two-dimensional manifold interpolation. And then in higher dimensions, we will see diffeomorphisms and then also isotropies of diffeomorphisms. But these we will somehow not really see in most of the talk because the tile will truncate them. And then in an extended series, what we want to do is to these objects, we want to assign some linear category, which usually, or one assumption people often make is that it's semi-simple, it has finitely many isomorphism classes of simple objects. So this is what some people call a two-vector space, and what I will call a two-vector space throughout the talk. This is also equivalent to the category of semi-simple separable algebras over the order, finite dimensional. And then to these Bordisms, before we assign linear maps, now we want to assign linear functors to them. And then these two morphisms filling in this set, we want to assign natural transformation. And composing, these two morphisms can be glued in two different directions, horizontally and vertically. And we ask that somehow the gluing of these manifolds corresponds to the composition of the natural transformation. And the question I want to talk a bit about is, what does it mean to be positive or reflection positive for these mappings? And for that, let me just say, it's easy to say what is a reflection. We have a Z2 action on the bottom category by organization reversal. There's a Z2 action by complex conjugation on this category of C linear two vector spaces. So a reflection series is just a Z2 equivariant function. But then what does positivity mean? And the way I told you positivity works in the non-extended setting is that we pick certain Hermitian structures, and then we ask them to be mapped to some other Hermitian structures we like. So Hermitian structure was really an identification between this orientation reversal and the dual. There's a nice way of thinking about this in the Bordism category. If you think of the object not just being an n-1 dimensional manifold, but living in some more small germ of an n-dimensional manifold. So there's some small extra direction here. There's a circle times R, and then there's some extra direction indicated by this arrow, which tells us how we compose morphisms. And then a Hermitian structure is telling us that orientation reversibility reverses this arrow on the circle is the same as taking duals, where duals reverses this arrow of direction we think about. But then, so if I take a dual, like somehow, the only thing I can do with this arrow is I can reverse it. But now, if I'm an extended theory, I should still think of my object as coming with these two directions, or being a germ in some now in some like here 0 plus 2 dimensional manifold, and these two directions tell me in which direction I compose my one morphism and in which direction I compose my two morphisms. Now, if I want to take a dual, what I do is I flip one of these arrows. But so, for example, I could flip this one. This would be a dual morph or something like the direction of two morphisms. But I can also flip the other arrow. So I can flip this one. And then what I can also do is I can reverse the orientation of my object. And here in the emission structure, I ask these two things to be equal, or maybe these two things. But if I'm in this extended world, there's somehow more things I can do. Because if I have this ambient directions I chose, which really just tell me how I compose things in my category, I can act with O2 on this. I can rotate them, I can reflect them. So really I have O2 many choices for how this looks. And in category theory, this choice tells me, as I said, what are the directions of my morphisms. But if I think about this physically, I'm just at a point in my manifold. There's really nothing which says, oh, this is where one morphism goes, this is where two morphisms. If it would be a Lorentzian theory, you might have a time direction, which somehow tells you, oh, there's one preferred direction, but there are definitely not two. So if we talk about Hermitian structures, we should somehow not pick one of these duals to identify it with, but we should identify it with all of them. And I mean, here also now somehow these things are fully dualizable, so I'm somehow using that also two dual. And this is what leads to this notion of an O2 Hermitian structure. And this is somehow the one thing one might object to, but I hope I at least motivate a bit. Now, we can just run the same story we did before, but with two categories. So we take B, some symmetric monoidal right categories, where every object is fully dualizable, and so it means it has left and right, it has duals, but also the evaluation and co-evaluation methods. And then from the Gaussian hypothesis, we know that the whole group O2 acts on the core of this category, and this action I just denote by taking. So it's not the dual in the previous sense, but it's this action which takes these generalizable. And then in addition, I allow my action to be twisted by some map for I pick some symmetric monoidal action of the group Z2. I take the determinant map from O2 to Z2, and I allow myself to twist this action. Obviously, you can twist with other maps, actions of O2. And the reason this works, I mean, you should be, at least in general, be a bit surprised that I can take two actions of a group on the category and then combine them into a new action, because generally this will not work. But the Gaussian hypothesis action has the property that it will commute with anything else which is symmetric monoid. So I can combine them, and then I can define these O2 Hermitian objects just as fixed points for this action. So this will now be a bit more technically. There are more coherences, there are more identification. So if we go back here at the bottom, what really matters in the oriented quadrant category is just the orientation of this full picture. And then if I do the bar, it reverses the orientation. If I flip these two things, it will also reverse the orientation. So they're all canonically identified. And even in the setting, there are no automorphic, there's no choices of the automorphic. It's not that hard. Also, from the Gaussian hypothesis, you know that you get these other tangential structures by taking co-invariants for the action of certain subgroup. So they will exactly glue in these Hermitian structures. So all I wanted to say is that in the bottom category, every object has such an O2 Hermitian structure. And this is not true in the frame world. Just because in the frame world, if I take this framing I rotate it, it will not be the same as the originalist. And there's also no action you can put on the category which will undo that. But in the oriented setting, if I would not specify anything, if I reverse the orientation of one of these arrows, or related to the original thing in any way, but if I add this reflection, then it's designed so that there will be a Hermitian structure. Now, you can also ask what are Hermitian objects in the category of two vector spaces. And this is where the small thing I use from this recent work, which contains a lot more, is that if I look at these things called bias two Hilbert spaces, which I will explain in a moment, then they are a specific class of O2 Hermitian two vector spaces. Similarly, you have Hilbert spaces where a certain class of O1 Hermitian vector spaces. So the definition is I take some two vector space H, and then it has some dagger structure. So I have something which takes an adjoint, it's complex antilinear, as the identity on objects and squares 2 to 1. And it has some traits. So this is a map from the endomorphism to the complex numbers, which satisfies this trace-like condition, which means if I have two composable morphisms G and F, I can somehow compute the trace in one way, or I can compute it in the other way. And then what makes this a two Hilbert space is this condition that combining the dagger operation and the trace, I can write down some pairing on these morphism spaces by composing the dagger and taking the trace. And the condition is that this is a Hilbert space pairing. It's always going to be a Hermitian pairing, but it's not generally a Hilbert space pairing. And examples of these are, for example, for group G. It's a category of unitary representations of G. So these are finite dimensional unitary representations, should be finite. Dagger is just the adjoint for these representations, and the trace is just taking the usual vector space. And this will be somehow what corresponds to diagonal theory. Also, every unitary fusion category is in particular treated. And then, as for the non-extended setting, what happens is that any reflection theory will preserve these O2 Hermitian objects. So what we can now ask, if I have a reflection theory, I have these preferred O2 Hermitian structures on points. I can apply my reflection theory to it. I will get some O2 Hermitian objects. So I will get, for every object, I will get some fixed point living in this space. And I can ask this to be a two Hilbert space. And if it's a two Hilbert space, that's how my theory problem. Now, here's something which is a bit different to the non-extended story. One thing is that for a Hermitian vector space, it's a property to be a Hilbert space, is that something is positive. Whereas here, what I want to do is I want to lift at the map from two Hilbert spaces to all Hermitian vector spaces. This map is not injective, but it's also not surjective. So lifting against this map is making a choice. So there's some positivity is not just a condition of my reflection theory, it's also extra data. It's exactly the extra data of how I lift against this map. This is some discrete set of data one needs to choose. So this is some data. And then in addition, there are some conditions on one morphisms, which I'm not going to spell out here. Now I can give the first theorem. If we look at two-dimensional, fully extended reflection positive series, they are completely classified by the two Hilbert space they have this point. So the composite hypothesis would tell you, oh, these oriented series are shown as so two fixed points for what they assign to the point. But here the two Hilbert space are in particular knows what the two Hilbert, what the fixed point is. And if I assign to the point the unitary representation like with G, I get unitary dagger fitness. Let me just mention some generalizations. Now I want to explain what happens if I pick other tangential structures still in dimension 2. So the first thing is that just reflecting is not going to be good enough to have Hermitian structures. So we somehow there are two things. So the whole story doesn't work for arbitrary tangential structures. You already see that with the Sweet-Hopkins story, because if I look at the frame Portland category, objects just don't have Hermitian structures. So the series somehow cannot even get going. So you need a certain class of nice tangential structures. And it seems to be, or the case where we can make things work, is if we have some stable tangential structure. So this comes from some group living over BO, where BO is the limit of ON where n goes to infinity. And then also just twisting by reflections is not going to be enough. So we need to generalize the star action by some action of the stable orthogonal group. On the level of Bordisms, we call this a higher spin action. We did in a recent paper with Cameron and Luke, where we somehow constructed actions of the stable orthogonal group on the corresponding Bordism group for stable tangential structure. And then for general things as, I mean, in David's talk, for example, the target would really be a super version of the vector space. And then we can somehow run the same classification. So in 2D, you find that the fully local spin TFTs, they are classified now by a super version of these biased vector spaces. So just this means that it's everything is now enriched over super vector spaces. The pairings give you super Hilbert spaces and so on. And in the example, for example, for a group with G with some element in its center, which squares x1, you can look at the unitary representation of super vector spaces where CX by the Kelvin. And you can also classify these unitary things for other tangential structures. There's a nice class which comes from what's called an internal fermionic symmetry group. I think Cameron talked about that. Cameron talks about on Tuesday, I think. So you can ask what are unitary TFTs with tangential structures coming from this internal symmetry group, and they turn out to just be unitary two representation of this group. So they are just given by acting with unitary functors on the two Hilbert spaces. So just doing representation theory for this internal fermionic group allows me to pass on to other tangential structures. One fun thing you can do is you can look at the invertible case. So I can just ask what are unitary invertible 2D TFTs with for some internal symmetry group K. So I have some choices. The first thing is what is the value on a point? There are two invertible super two Hilbert spaces. One is just the category of super Hilbert spaces. The other one is the category of modules over Clifford 1. So I have some choice, which is H0 of KZ2. Then for each group element, I need to act with some unitary functor. So I either act with tensor with C or I act with tensor with the odd line. So for each K, I get some choice in H1, KZ2. And then there are some coherent isomorphisms, which live in H2 of K with coefficients U1. And these are, if you would try to compute this using Bordism groups, you can, for example, run the idea Hertzebus spectral sequence, and then you would get these three terms and some compatibility conditions. And these are exactly the compatibility conditions we get from us as a unitary representation. In my last 2 minutes or so, I will say a bit about what happens in higher dimensions. So this is, I mean, the results in the previous slides were already work in progress, but most of it is done. This is a bit more further in the future. So there's also some like technical things with the setup to be worked out, but at least there's a story on how this should generalize now to arbitrary. And we have at least somehow we have proofs of our theory. We just don't have like the perfect setup where to do this at the moment. But so what we start with is some fully dualizable M category. This just means each object has duals and any morphism has duals itself. And then the cobordism hypothesis tells me that ON acts by taking these generalized duals on the core. I can define ON emission objects by just twisting this dual action by some bar action, which we usually construct from some stable tangential structure, some X mapping to BO as a. This is constructed from O acting on C, which generalizes complex conjugation. And if I have some stable tangential structure, I can define this higher spin action on here. The point will always be an ON Hermitian object. Somehow this is by construction of this action. And this is also where we use stability, which is to construct an action which somehow exactly cancels the action of the cobordism composer set. So there's a point, and then if I want to classify TFTs in some target to talk about unitarity, I need to first pick a class of ON Hermitian objects alike. These are what I would call my somehow unitary objects or n-Hilbert spaces. And then the statement is that the space X acts on the unitaries of this category. So these are these referred emission objects, and taking fixed points for X is classified as unitary topological field series with this path. And what I want to highlight here is that there's some type of stability happening. So generally, the cobalt hypothesis would tell us we should take Xn fixed point, where Xn is somehow depends on n, and there's a pullback of this to BON. But in our result, somehow the whole thing we take fixed points for is a stable version of it. So enforcing unitarity and sometimes adds some stability to the theory. And that was already observed in the invertible case by Reed and Hopkins. Also now we can ask what are invertible series descending. So we pick as a target this shift of the Anderson dual. Then the theorem says it's fixed points for X. So this action is by the inverse of the J homomorphism. But if I take fixed points, I can also, if I map into fixed points, this is the same as mapping out of co-invariant. So I can do co-invariant, and then this is the stable version of the Maxim-Tillman spectrum. So this is somehow how this reduces to the invertible case and gives you back this result of Reed and Hopkins. Okay, I'm also done. So thank you for your attention.
So here we sort of incorporate the location of symmetry and topic when categories features of the others based on symmetries are all symmetry almost.
Maybe I don't think I have anything useful to say about that. I mean, this is the things we are doing are extremely homomorphic. You could try to work with these things called smooth families, where you do like manifold parameterized over, I don't know, divide manifolds, things like that. I have no idea what was that.
More questions? So this one, well, if I want to do this not so extensively, like the information structure very long for people.
I think they still usually just packages in a less, like in a more coherent way. So you were saying, somehow there's this extra choice you need to make, but it's more in the framework, so you give it as extra data in the setting, and then if you ask, so it's a bit more compatible. So I should also say that this says that in the cobalt hypothesis, the setting the starting point are framed manifolds. Here, framed manifolds don't work because they will not lead to any notion of unitarity, but what replaces them are stably framed manifolds. So for stably framed manifolds, this just tells you that the unitary DFTs are exactly specified by some Hilbert and Hilbert space there or something.
Let's say a secret again. Back at 10 foot.
I'm sorry. I mean, it's not as a category itself, but as a category. Somehow it's the free